So chapter 20 is also about numerical integration and functions. And it's called Richardson extrapolation. And it's a subset of something called ROMBERG integration. And the concept is very easy. So the concept is you can combine two numerical estimates of the integral to obtain a third estimate which is more accurate than either of the first two. So you can use two low accuracy methods, combine them together, and get a higher order, a more accurate estimate of the integral. And the answer, I mean, basically the whole thing is just this one equation. So here, this I is the more accurate, which I labeled green. And it's using two estimates of the integral with a different step size. You see there's h1 and h2. So that's the key there. You have to have two estimates, two lower accuracy estimates with different step size. You can combine them in this very easy formula, and the answer will be a higher order accuracy, more accurate estimate of your integral. So another requirement is that h2 has to be half of h1. So these step sizes are related to each other. So that's kind of the end of the chapter. So to get to this end, we have to understand the derivation. And the derivation starts here. What it says is that your true integral I is composed of the estimated integral value plus some error. So this is just some truncation error because you're approximating the integral with a straight line or with a parabola or some other ordered polynomial. Now if you make two different estimates of the same integral, so the integral is I, that's the true value. You can make two estimates. So here's number 1 and here's number 2. The only difference between these two estimates is the step size. One integral has the step size h1, and then the other integral has a step size h2. So for example, you're using trapezoidal rule for both of them, but one has step size h1, the other one has step size h2, or say composite trapezoidal rule. If you add the estimated value plus the error, you should get the true value, right? Same thing for this one. You add the estimated value plus the error for the second estimate, you should also get the true value. So these two should be equal to each other. And since we're pretending like we're using the trapezoidal rule, you'll remember the formula for the composite trapezoidal rule for the error. So this is the formula for the error, and in this formula, B and A are the range, right? So you have like your integral goes from A to B. So you're integrating on this range. So for both estimates, your range is going to be the same. Only the step size, like the size of the bins that you're breaking up this range into, that would be different. But the range itself stays the same, so A minus B. So it's like limits of integration, A and B, right? So we make an assumption that the second derivative of this integral is a constant. This is an assumption. And if you assume this, then the two errors of the two different estimates, so this one and this one, should be related by the ratio of their step sizes squared, because that's the only thing that really changes between the two errors, the step size. The constant second derivative would cancel out, and the b minus a over 12 would cancel out because those are all the constants. What you can do then is you can rearrange this equation to solve for E1 in terms of E2 and the two step sizes. And once you can express one of the errors in terms of the other, you can simply plug it in to here, for example. So this was your error 1, and this was your error 2. And that's what I'm showing here. So you just take this equation here, equation 21, and you plug in for E1 the equation which contains E2. So basically, now you only have one error term on both sides, the E2. So it's here and here. So it's one equation, one unknown. You're trying to solve for the error, basically. So you can rearrange this equation to express the error in terms of the integrals, the integral estimates, and the step sizes. So basically the idea is to eliminate this error. So now what we do is we take this expression for the error and we plug it into the very first equation, which was here. So we want to get rid of that error term. We just want to leave it in terms of integrals and the step sizes. So when you plug this in and you rearrange, you're going to get this equation, which we call the improved estimate of the integral. And this one has the two different integrals with the two different step sizes, and then the ratio of the step sizes. So in this case, you haven't made any assumption about the step sizes. You just have the two different step sizes. But this approach, they also assume that one step size is half of the other one. So when you make this assumption, you can actually, like this part here, you can express it. I mean, the step size will cancel out, and you'll just have a constant in front. So this in the red here is the most simplified version. But the idea is that, like I said, you have an improved, which is this one, estimate of the integral by using two lower order estimates together. And the difference between them is just the step size. So it's a very easy topic. And you can also do the same thing to derivatives. So the next chapter, chapter 21, is going to be about the derivatives. So you can also use a similar formula to improve the accuracy of numerical derivatives. So are there any questions about this one? So if you understood nothing and you only want to take one part away from this chapter, it's this equation, right? So you can use this equation to improve the accuracy of your integral estimate. Alright, so the next chapter is numerical integration, chapter 21. So for this one I have a little PowerPoint. Now we have to wait for the PowerPoint to open. Alright, so sometime back in the semester we talked about the three different ways to estimate the derivative. So this was actually in chapter 4, we kind of skipped over that. But we did mention this. So if I'm trying to estimate the derivative at point I, so this point here, you need, derivative is slope, right? That's what you were taught in high school. So you need 2 points to estimate the derivative, right? So you have multiple choices of what you can do. One thing you can do is you can do the forward difference. In the forward difference, you use the point I, which is where you're trying to, I guess it died. Alright, so you're using the point I at which you're trying to estimate the derivative. The second point is going to be the point I plus 1, which is forward from point I. So it's this one. And that's called the forward difference. So you would estimate this slope here, which is in red. But the true one is actually this one. So second thing you can do, second thing you can do is you can use the middle point, which is the point where you're trying to estimate the derivative, and you can use the backward point. So you can take a small step back, right, and use the backward point. So your estimated derivative would be this, but the true one is actually this one. The third thing you can do is to estimate the derivative here, you can actually use the two neighbors. So you don't use the middle point, you use the forward point and you use the backward point. And then your estimate becomes like this, which is actually closer to the true one, which is a little bit tilted. But of course this depends on the shape of the function. So the way this is drawn, the true derivative depends on the shape of the function. So in this chapter we're going to talk about how these are derived, how these formulas are derived. Right now I'm just kind of using like simplistic visual arguments, but there's a formal way to derive this. This slide so it's trying to estimate the derivative of a different function. In this case it's a parabola, and instead of drawing them all on the same graph, it draws each one on a separate graph, but basically it's showing you the same idea. So here the green is the true derivative, and then your estimate is the forward derivative. In the middle pane, the true is the green derivative, the estimate is the backwards, so you're using the backwards slope, and then in the third one you're using the two neighbors to estimate the true derivative. So visually it's very easy to understand, right? You either use the forward neighbor and the point, or you use the backward neighbor and the point, or you just use the two neighbors and not the point where you're trying to estimate the derivative. But to understand the derivation, we first have to understand Taylor series, because the derivation uses the Taylor series. So the Taylor series, what it does is it tries to estimate the function at some new location where you know nothing about the function. So this is important. At some new location where you have nothing, you know nothing about the function at that new location. And you're going to use information at some known point, which we call the current location. So at the current location, you do know something about this function. But you're going to try to estimate the same function at a different location where you know nothing about it. That's what the Taylor series does. So I have a little YouTube video. Let's see if it will play. No, it doesn't want to play. Play. Alright, so if it doesn't play from here, then save media, animations. So if it doesn't play from here, then I'll play it from Moodle. Alright, so let's turn up the volume.
Here's a typical exam question. This problem actually gives us some of the motivation for Taylor series. A small handheld calculator can't possibly store.
Let me see if I can make it full screen.
For every
She did that so fast.
Alright. Skip the ad.
every possible value of sine. What is needed is a formula, and Taylor series gives us that formula. Since Taylor series is a formula, most of the work in giving a solution to the exam question is in remembering the formula and knowing how to use it. To understand Taylor series, imagine this game. I've grabbed a function and pinned it onto cardboard, and then covered up most of the function with green cardboard. In fact, there's only one point that we can see of the function. I'm going to call the x point a equals pi on 2. That's where we go up from, and you can see here that the value of f of a is equal to 1.
Okay, so this is the known point. So a equals pi over 2 is the known point. This is where you know something about the function. Let's put the phones away, please. Thank you. So you know the x value and you know the y value at this location. Let's see what happens next.
Now I'm prepared to reveal any sort of information I have about the function at that point to a group of primary and high school students. And the aim is that they are going to try and work out a formula for f of x. So x could be anywhere. It must work for basically all x, but I'm just going to put x here for the purposes today.
So x is the new point where you know nothing about the function, and you're trying to estimate the y value of that function using the knowledge at the known point a pi over 2. So is that clear? You're trying to estimate the value of your function at the location x where you know nothing about the function, and you're going to use the knowledge of point pi over 2, x equals pi over 2, where you do know something about the function.
We start with the primary school student. And he reasons, he says, well, all I can see is that point there, 1, which is FA. So I'm going to say that f of x equals f of a. Now we come.
So basically, like, what can you do? How can you estimate the y value of the function at location x? The simplest possible thing you can do is you can say that the function is not going to change, it's going to stay the same. So the y value at x is the same as the y value at pi over 2, right? So this gives you the first term of the Taylor series. So that's why it says f of x is equal to f of a.
To the next old student, and he says, well, I've learned about slope. You said you'd reveal everything about the curve at that point, so you'll tell me the slope. So I suppose if I assume that the slope is constant, then if the slope is positive, then f of x will be up here somewhere. And if the slope is negative, then f of x will be down here somewhere. The next student says, well, we can actually work this out. We know that the slope is the derivative, f dash at the point A. We know that the run here, this distance here, is x minus a. So we can work out the rise, this little bit here, and that will be x minus a times f dash a.
Okay, so the next more advanced thing you can do is if you know the slope of the function, so it's not staying the same, right? It's not, the y value is not going to be the same as at the x location as at pi over 2. So if it has a slope, if it tilts upwards or downwards, and you know what that slope is at point A, you can use that to find the delta y, right? So the delta y is going to be the slope times delta x, because we know that the slope is delta y over delta x, right? So let me write that down. So the slope is equal to delta y over delta x, right? Well, it got cleared.
We can just add that on.
Let me try it again. So the slope is equal to delta y over delta x. So if you take the slope and you multiply by delta x, these guys will cancel out and you'll end up with delta y, right? So that's what they're doing. This thing here is equal to delta y between these 2 points. So between point A and point x. So you can use, if you know the slope, the first derivative at this location, point A, you can use that to estimate the y value of the function at point x.
So at this point we've got fx equals f of a plus x.
And this gives you the second term of the Taylor series. So this is the second term, and this is the first term.
X minus a times the derivative of f at a. So then the next student says, but I've learned about the second derivative. And if the second derivative is positive, that means the slope will increase when we go from a to x. And so f of x will be even higher, it'll be up here somewhere. Simply, if the second derivative is negative, then the slope will start to decrease and f of x will be down here somewhere. but I can't work out what I should multiply that second derivative by. I know that it should have the second derivative, but I don't know what to put there. So I'll just put plus question mark times the second derivative of f at the point A. So then the final student says, well, I can't help you with what the question mark should be, but I know that you can extend the argument. So we should actually have something to do with the third derivative, the fourth derivative, and it goes on and on forever. So we can start adding these plus the a question mark times these higher derivatives at the point A.
So basically it's an infinite series which has successive higher and higher order of derivatives for each successive term. And if you have the whole infinite series, that will give you the exact value of the function at location f, or at location x. But we can't do infinite series in calculators and computers, so we usually truncate the series.
And these higher derivatives at the point A. Okay, we're pretty close to a definition of the Taylor series and then being able to solve the exam question. Here's the equation that we have got so far. So now let's replace the question marks by the correct expressions that we should put before the higher derivatives. So how do you remember this in the exam? Well, we've already seen the first part comes from very simple, the high school mathematics. The FA plus x minus a times f dash a. We've also seen how we must have in the formula somewhere these pi derivatives, second, third, fourth derivatives. The expressions that are before derivatives are linked by the process of integration. So we know the first one, x minus a. If we integrate that with respect to x, then we get x minus a squared divided by 2 factorial. And that's the expression that we should put in front of the second derivative. We then integrate again. So we integrate x minus a squared divided by 2 factorial with respect to x. We get x minus a cubed on 3.
So this just tells you how to memorize the terms or how to derive them yourself. But the point is that you should understand that the Taylor series, the point of the Taylor series is to estimate the y value of the function at some new point x using knowledge of the function at some known point a. Right? So you use the derivatives of the function at a, and then you have this kind of step size. So the difference between the new location x and the old location a. So that's what the Taylor derivative does. So the next video is where's the next video? Here. So the next video shows how to derive the forward and the backward difference.
Get started then with numerical differentiation. The first thing we can do is just look at the definition of the derivative that we got in calculus. This is the difference quotient definition of the derivatives. It says f prime of x is equal to, was defined as, the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Now you may say, well, what happens if delta x is not 0, if it's some finite value? And we can answer that question by going to the Taylor series. But before we get going, let me just make clear what we're going to have here. So this is just a number line. And let's say the point, some point that we care about is, let's call that point x, x of I. And then a point ahead of it, we'll call that x I plus 1. And then some point behind it we'll call x I minus 1. And this derivation is for equally spaced data, and so that will require that xi minus 1 and xi plus 1 are the same distance from xi. Anyway, so doing that, we can get right in and then look at the Taylor series. So this is the generic formula for the Taylor series. We cover this in Unit 1. F of x is equal to f of a
Okay, so this here is just a definition of the Taylor series. Same as what we saw in the previous video, right? You have some known point A, and you're trying to estimate the value of the same function at some new point x. So this is just a definition of the Taylor series. And he's going to have three different points, xi plus 1, so the forward point, the backward point, and the point itself. So what does he do? The first one he derives is the backward. So xi is going to be like the point A, right? So he plugs in xi here, here. So everywhere where you see A, that's going to be xi, the middle point, right? That's the known point. And the new point, where he's trying to estimate the value of the function, is going to be this one, the backward, xi minus 1. So that's why it says xi minus 1 here. This is the new point.
Plus f prime of a over 1 factorial times x minus a plus f double prime of a over 2 factorial times x minus a squared plus f triple prime of a over 3 factorial times x minus a cubed, and so forth. Now, recall then, though, that f of x, so this is f evaluated at any point. That's going to give us, because we're going to get some function that will give us x evaluated at any point, and we're expanding it about the point A. So A is the known point, and x is the unknown point that we're trying to figure out. And so then this is the approximation, and you see the higher order derivative terms. We've got a first derivative, a second derivative, third derivative, and so forth. So we can write this. We just let the x that we want to know, x equal xi minus 1, and then a equal xi, and we just plug that in then, and that's where we get this formula from, right? f xi minus 1 then is equal to f of xi plus f prime at xi over 1 factorial xi minus 1 minus xi plus f double prime xi over 2 factorial, and so forth, okay? Now, what we can do is continue writing things out. Well, the first thing, though, is we'll define h as xi minus xi minus 1. So that is just this distance here. We'll call that h. And again, so this is the backward difference. We're only going to need xi minus 1 and xi to do this approximation. And we're going to plug in then for xi minus 1, xi minus h. And you can see that from here. It's just rearranging this, so xi minus 1 is equal to xi minus h. And that'll let us represent this in terms of h, in terms of the distance here. Okay, so you might also call that h delta x, okay? So we say f of xi minus 1 is equal to f of xi, f prime xi over 1 factorial times h, f double prime xi over 2 factorial times h squared, f triple prime 3 h cubed, and so forth. So you get the idea. Then what we're going to do.
All right, so he defined the step size like this, right? We're doing a backwards derivative, so we're stepping backwards. The step size is xi minus the backwards point xi minus 1. So what he does is he just replaces this thing in the parentheses with minus h, right? It's just the same thing, just off by a minus. And he plugs it in into all these parentheses, and that's how he goes with from this equation to this equation where you have h's in them. So the next step that he does, we're trying to find the formula for the first derivative. That's this term here, right? So he basically brings this term to the left-hand side while bringing this term to the right-hand side, and then he solves for the f prime to find the formula for the derivative.
Let's move down here a little bit. What we're going to do then is take this term. We want to find the derivative. And so we're going to take this term, the derivative term, and we're going to take it to the other side of the equation. And then we'll just take this term and we'll move it back to this side of the equation. And so in doing that, then we get, this already had its minus sign in front of it, so we just move it over. But then we have to get rid of this h. So we just say then f prime of xi is equal to 1 over h times f of xi minus f of xi minus 1 plus f double prime xi and so forth. So we have all these terms in here. So
Alright, so you're looking for the derivative, right? The formula for a derivative. So here's the formula for the derivative, but it has an infinite number of terms. So what can you do to simplify it? What? Consider them what? Error? Yeah. So you can truncate your infinite derivative by throwing away terms, right? So if you look at this, it's basically delta y, which is what this is, fxi minus fxi minus 1, divided by the step size delta x. And that's the formula that you know for the derivative, right? So that's where it comes from. It comes from truncating the Taylor series. But what if you wanted to have more accuracy? What could you do? You could keep some of the terms, right? You could keep the second derivative term, or you could keep the third derivative term. So your formula for the first derivative can actually be different depending on how much accuracy you want, right? So the one that you always see is the most simple one, but it's also the most inaccurate one. But you can actually have more accuracy by having more terms. This one doesn't really do that. It just shows you how to get the simplest formula. But the procedure will be the same. You use the Taylor series, but you just keep more terms.
But then f prime at xi is equal to 1 over h times f of xi minus 1 over h f of xi minus 1. Now we have all these terms here. These are our second and third derivative terms. Now we can just throw those away. This keeps going, and we just throw those away. Now, when we throw them away, we incur error, and so we'll have some error by doing that. But that's where it's an approximation then. So when we do that, we get f prime at xi equals f of xi minus f of xi minus 1 over h plus this error on the order h. You can see the order h, that's the largest term there. So we have error order h. Then we get f prime at xi is equal to f of xi minus f of xi minus h, because we're just substituting our derivative, or excuse me, our xi minus h back in for xi minus 1. That's what we have here, all over h. And if you notice, this is the backward difference method, where we just say h equals delta x. We could have used delta x instead, but that is then the backward difference derivative. Now we can do the forward difference derivative in the very same way. So let's go to here. Okay.
So for the forward difference, the procedure is the same. You're still using xi as the known point, right? So this stays the same basically. But now your unknown point, where you're trying to estimate the function f, is the forward point, xi plus 1. And your h is also different. in the first one, in the backward one, h was equal to xi minus 1, right, the backward point. But in this case, it's the forward point minus the middle point. Otherwise, it's the same. The procedure is the same.
The forward difference is just the same, except instead of plugging in to our original equation, remember we plugged in the x we wanted to know, we plugged in xi minus 1. We could just then plug in xi plus 1 instead of xi minus 1. And the derivation continues the same way. We write it all out. We take this term to the other side, and we take then this term to this side. Yes, right there. We rearrange it. We throw away the higher order terms. We incur this error, and we get our, and then we get our approximation to the derivative. We can compare those to our definition of the derivative that we had before, and we see that it's just exactly the same thing. F prime of xi, this limit is delta x goes to 0, so we don't have this limit term here, but this term here, right here, is exactly the same then as this term here. So
Alright, so the next video...
we showed the forward and backward.
The next video is going to show how to use the forward and backward formulas to derive the centered. And the centered is the one that's really interesting because it has a different order of accuracy. But they use the two results which we just showed how to obtain, the backward formula and the forward formula, and then we use them to solve for the centered difference approximation.
Difference approximation is the derivative. We showed how those are derived from the Taylor series. We may as well just show then the center difference approximation as well. Using the notation that we used before with the h, having defined h, we can write out the Taylor series for x plus minus 1 and x plus 1, x minus 1 and x plus 1. And when we do that, this is what we get. So you can just compare that to what we showed previously, the same thing. We just have x minus 1 and xi plus 1. We can solve these both for minus f of x. So in order to do that, we'll just bring this to this side, and then this term then to this side. So same thing over here, bring this to this side, bring this to this side of the equation. And when we do that, we get n minus f of xi is equal to minus f of xi minus 1 minus f prime at xi over 1 factorial times h plus f double prime minus f triple prime and so forth. So we get these two now. You can see they look very similar, and that's good. So what we're going to do is we're going to combine them. We can just combine these two equations, but in order to do this, h has got to be the same, and h then is going to equal to f of x plus or minus delta x, right? If you remember the number line we had, xi plus 1, xi minus 1, this is our h, and this is our other h, and so those have to be the same. If those aren't the same, when we do this step and combine these two equations, it's not going to be valid, and so that's why we have to have an equal step size for this. So this method is for equal step size. So when we combine these, then we get this equation. All right. So
basically, he takes the backward and the forward equations. He rearranges them so the first term of the Taylor series ends up on the left-hand side, and then you can eliminate this by subtracting one equation from the other.
So we combine them, we got that equation. We should notice a couple things. Okay, this term went away, right? The other thing we should notice is that when we combine these equations, we subtracted this one from this one, and so these terms, these terms went away, obviously. These terms both stay. What happens, though, is these terms get wiped out completely.
So this is key. In the derivation for the centered finite difference equation of a derivative, right? The second order terms disappear on their own. They just cancel out. So you don't have to truncate them. You actually truncate the third order derivative terms. The second order derivative terms, they cancel out naturally. Which means that your accuracy is where you truncate. You truncate the third order derivative terms, right? In the backward and forward finite differences, you truncated the second order derivative terms. But here the second order derivative terms cancel out naturally, so you don't truncate them. You truncate one order higher, which is the third order derivative terms. So because of this, the centered finite difference equation is going to be more accurate than the backwards and the forwards. So it comes from a derivation.
And then our expansion becomes minus fxi plus 1 plus fxi minus 1 equals 2. So we have this times h and this times h cubed. When we rearrange that and solve for f prime at xi, we get f prime at xi, or negative f prime at xi, equals 1 over 2h times f of xi minus 1 minus f of xi plus 1 plus 2f triple prime h cubed. So if you look here, we have the h cubed term here, and of course that's going to cancel with that h cubed. We can put in the 1 over 2h into these first two terms, and one of those h cubed is going to cancel down to h squared. So we're going to have f triple prime of h squared plus these higher order terms. And then our approximation is going to be accurate order h squared. So it's going to be accurate order h squared.
Come on.
H squared.
Alright, I'm trying to pause it at the end.
Is going to be accurate.
Alright, so this term is the one you're truncating, not this term. This term just cancels by itself, so you don't truncate this one. You truncate the third order derivative term, so your accuracy is h squared, OH squared. That's the terminology for the accuracy, which says up to which term the equation is accurate. So if you look at the equation for the centered finite difference, you'll see that the y values are the backward point minus, so actually here he says they switched inadvertently, so it actually should be the forward minus the backward, not the backward minus the forward. And then at the bottom, you have the delta x, right? But your delta x is now all of this thing. So it's double of the forward difference and the backward difference. But because you're making this formula in terms of h, which is just a single step size, they put it number 2, so 2 times h. But it's actually just signifying this interval, which I labeled in green. So yeah, let's close this. If we go to your book, there are tables. So there are tables in your book given for, this one is for the forward finite difference. So basically, this one is the formula which is less accurate because you truncated more terms. This formula is more accurate because you kept the second order terms instead of truncating it. So you see the accuracy is higher. But the penalty is that you have to use more points. So you can estimate the first order derivatives, you can estimate the second order derivatives, third order derivatives numerically, and they all come from that Taylor series, and the accuracy depends on how many terms of the Taylor series you keep. I'm not sure why the screen is not coming back on. Slowly, yeah, coming back on. Alright, so basically here they give you equations for this table here is for the forward finite difference formula. So here you have the less accurate forward finite difference formula for the first derivative, where you truncate all the terms after the first derivative in the Taylor series. This one is where you keep the second derivative term in the Taylor series and you truncate everything after that, so the third order derivatives and so on. So it gives you a more accurate answer, it gives you a more accurate estimate for the first order derivative, but you have to use more points. So you're going forward, so you have one forward neighbor, which is a xi plus 1, and you also have a second forward neighbor, xi plus 2. So you have to have more information about your function. For the less accurate, you only needed to know the y values at two different locations, right? Xi, where you're trying to evaluate the derivative, and one forward neighbor. For the more accurate formula, you need to have an extra forward neighbor, xi plus 2. You're still trying to evaluate the derivative at xi, still the first order derivative. You're still using the forward finite difference approximation, but you're using more points. And I actually have a derivation on the Moodle handout, so let me go back to Moodle. This one. Okay, so here's the derivation. Here's the forward Taylor expansion for evaluating the function at the forward neighbor, right? At xi plus 1. You can solve this by getting rid of the second order derivative if you truncate everything after that, right? You can solve this to give you this equation here. That's the one you know and love, right? The simple equation for a derivative. But if you don't truncate this term, so if you truncate it, your order of accuracy is 0 or OH. But if you don't truncate it, your order of accuracy is going to be OH squared. So if you do not truncate it, if you keep this term here, so now you don't truncate, so this is your formula for the first order derivative. These points, you know, these are just your y values, right? But what do you do about the second derivative in this equation? Again, you're trying to avoid doing calculus, right? This is numerical methods. You're trying to avoid doing calculus, so you do not want to calculate the second derivative analytically. So what you're going to do is you're going to take the equation for the second derivative from numerical methods. And this was given to you in chapter 427, or sorry, chapter 4, equation 427 on page 125. This is a low order equation which tells you how to calculate the second derivative numerically. So you basically take it and you plug it into here. And when you simplify that, you will get this equation, which is a higher order first order derivative. And that's what you see in this table here. So the difference with this equation is they kept an extra term of the Taylor series, the second order derivative term, right? And then to evaluate that term, they used this equation basically here. So it's a low order accuracy equation for the second derivative, and they just plug that in to get this equation. They plug that into the Taylor series to get the more accurate first order derivative equation. So the table just gives you all of these equations. So these are all forward finite difference formulas for the first derivative, second derivative, third derivative, fourth derivative, and for each case you have a low order where you truncate everything except for the everything except for the first two terms, and here you truncate everything except for the first three terms. And then this is the same. You have a low order accuracy and a higher order accuracy. Low order accuracy and a higher order accuracy. And always the penalty is that you have to use more points to get a more accurate estimate of the derivative. So for example, for the fourth order, here you're using 4 forward neighbors, while here you're using 5 forward neighbors. Right, here's your xi plus 4, and here's xi plus 5. So these were the forward finite difference formulas. There's another table for the backward. So this table is for the backward finite difference formulas. Again, you have your regular one where you truncate at the second derivative, you truncate that term and every term after that. But if you don't truncate it, if you keep this term, you get this formula, which is more accurate. So it's more accurate, but it's using an extra neighbor, but in this case you're using backwards neighbors, not forward neighbors, because this table is for the backward finite difference formulas, right? And then you can do the second derivative, third derivative, and fourth derivative also. So these are all backwards, using the backwards neighbors. Finally, you have a third table where these are the centered finite difference formulas. So again, compare the accuracy here to the accuracy here. As I told you, the centered one is always more accurate than the forward and the backward. This comes out of the derivation, where the second order derivative terms in the Taylor series just cancel naturally. So you don't truncate them, they just disappear by themselves. You truncate the third order derivative terms of the Taylor series and everything beyond that. Because of that, you have a nice bonus that the centered finite difference is more accurate than either the backward or the forward one. But you can also, just like here, you could improve the accuracy by using more neighbors. Same thing happens here. Instead of just using the forward and the backward neighbor, you can use the forward and the backward, and then you can also have the one more backward and one more forward neighbor. So instead of using 2 points, you use 4 points. And your order of accuracy goes from h squared to h fourth. So the centered difference formulas are always more attractive, because even though you're using the same number of points, like here you're using 2 points, right? Here you're also using 2 points, but the accuracy is much higher. So same as before, for the centered finite differences, you can get the first order derivative, second order, third order, and fourth order. So you can estimate those numerically without doing any calculus, simply by knowing the y values, which are at the top, and then the spacing. So the spacing between the neighbors has to be equal. That's why you can express it in terms of h. But without doing any calculus, you can estimate these derivatives using either the forward, the backward, or the centered approaches. And depending on what kind of accuracy you want, you can use more and more points to get more and more accuracy. So if you wanted even higher accuracy, I'm sure there are formulas which are derived for higher accuracy, which use even more points, even more neighbors, right? So you can just keep increasing the accuracy by using more and more neighbors. So again, the chapter is not that difficult. If you didn't understand anything, just use the tables, right? The table just gives you the formulas, just use the tables. Like I said, remember we talked about the Richardson extrapolation, where you could increase the accuracy of your integral estimate by using 2 different integrals, right? So here's the formula for this Richardson extrapolation. You had one integral estimate and another one. The only difference between them was the step size. Here the step size is h1, and here the step size is h2. And we made the assumption that h2 is half of h1. So we assumed that they're related to each other by a factor of 2. And if you make that assumption, you can get a higher, so I'll circle it in green, a higher order of accuracy estimate of the integral. Similarly, the formula is exactly the same. You just replace integrals with derivatives, so d stands for derivative. You can improve your estimate of the derivative by taking 2 lower accuracy estimates of the derivative with a different step size. One has a step size of h1, the other one has a step size of h2. You combine them into this formula, and you get an improved d, which is going to be a higher order of accuracy than the 2 individual derivatives that you used. So there was an example 21.2 where they kind of prove that to you. For unequal space data, which was your homework, the idea is again really simple. You just fit a Lagrange polynomial to your data, and then you differentiate the Lagrange polynomial. So with numerical methods, the idea is always the same. You want to avoid using the actual function. Either it could be really difficult to take a derivative of that function, or you just don't know what that function is. So instead of using the actual function, you use something simpler. So you fit a straight line through it, or you fit a parabola through it. And once you do that, your math becomes much simpler. You can differentiate a parabola very easily. You can integrate a parabola very easily, right? So you just fit a simpler order polynomial or a simple order polynomial through your data, and then you can manipulate that polynomial because now it represents your data. So for unequal space data, they just fit a Lagrange polynomial through that data, and then they differentiate that polynomial to give you the equation which you used on the homework. So it allows you to estimate the derivative anywhere between 3 points. The points do not have to be equally spaced because you can do interpolation easily if they're not equally spaced. Interpolation does not require that your points are equally spaced. And the accuracy is the same as the center difference, but it requires an extra point. Now you have 3 points instead of 2 points. And then the final thing that they say, and this is shown here. So the final thing that they say is they basically tell you which one is more sensitive to error in the data, differentiation or integration. And the answer is that differentiation is more sensitive to the error. So for example, here they show you some data, kind of looks like a parabola, right? So if you differentiate the data, you get a straight line. But if you have that data, it still looks like a parabola, right? If you fit something through it, it looks like a parabola. But now it's not as nice. It's like a little bit has some error in it. So it's a little bit variable. So if you differentiate now this data, it does not look like a straight line. It looks much different, right? So the differentiation is much more sensitive to measurement error. Integration is less sensitive. And the reason for this, they say here, so differentiation is a subtractive, while integration is a summing process. So in a summing process of integration, the positive and the negative errors tend to cancel out. So it's more forgiving. In differentiation, this doesn't happen. So differentiation is more prone to error than integration. So that's a good conceptual question for the final. And partial derivatives we're not going to cover. It's too complicated. So then the end of the chapter 21 is the diff. So the diff command in MATLAB, all it does is it finds the differences. So if you have like a vector of points x2, x1, x2, x3, x4, what it's going to give you, so let's say this is your vector x, right, in MATLAB. If you say diff of x, what that's going to do is it's going to give you like x2 minus x1 for the first point, x3 minus x2 for the second point, x4 minus x3 for the third point. But the number of points in your answer is going to be one less than in your original vector, right? Because you're finding the differences between these points. So you could evaluate derivatives if you have the y values, right? So you could do diff, sorry, this should be y over diff of x. So you could find like differences in y's divided by differences in x, and this can give you the derivative at all of the points that you have stored in the vector. And that's what they show here. And of course, you have to do the dot. All right. You have to do the dot division because you want to do element-wise operations. And then they also give you another function which is called gradient. So in the gradient function, what it does, it's a little bit different. So for the first value, it takes the difference between the first and the second value. For the intermediate values, it uses the centered difference, so it uses the two neighbors, the two adjacent neighbors, to calculate the center difference. And for the last value, it's going to calculate the difference between the two final values. So the result is basically using centered differences, which are more accurate for the intermediate values, but then using the forward and the backward for the two values at the ends, at the beginning and the end. So this is everything that chapter 21 covers. It does tell you about some other MATLAB things. I think it does contour. Yeah, so it shows you how to make a contour plot and also do a quiver plot. So the contour plot we've already seen. What the quiver plot means is like putting these arrows which are showing you which way the gradient is facing at each point, at each location. So that's called a quiver plot. Alright, so let's do our homework assignment in MATLAB. And then if you finish early, it's just basically programming that equation in. I think the only difference is again, just like in the gradient command, for the first point, for the beginning of the array and for the end of the array, you have to do something different. But then for the intermediate points, you do it the same for all the intermediate points. So it's just programming that equation in, and then you have the if-then statement for the beginning of the array and for the end of the array. So once you finish that, if you want help on your project, I can also help you with the project. And let me make a submission on Connect.